Recording. Yeah, okay. Okay. That's good. Recording. It's recording. Okay. Okay, last week we did, and that's for the first year program. You remember this, Yara, from last year? And I'll just analyze it. Yeah, there it is. Oh, it's this one. So Kadiri, you built this in PSpice. And I'll separate the signals. Just make it a bit more clear like this.
Sir, can you make it a bit? Yeah, I was gonna say, can you make it thicker?
I'm working on it like this. Just ask anything you like, and I'll try to make it more clear like this. You can see it now?
Yep.
Okay. So I can do it like this, and you see the output, and we can see the schematic at the same time. This is the output, and here we have the schematic. To change them, this one first, second one. Okay, so this is a schematic from the first term. The students learn to build a relatively simple oscillator schematic. So what happens here, you have a 10 volts, and you remember, you guys, the current second year students did this last year. They also built this on the breadboard, and yeah, you have to be aware that when you're going to build this, in PSpice here we used for the transistor, for instance, the Q2N2222, and in reality that's the BC237. We have this transistor here in stock. Yeah. I think for Kadiri you can go and build this. Yeah, if you want. Your own breadboard? Yeah. You have it with you?
No. Oh yeah, I do.
So if you want to, you can sit on the lab table, and you can start building on your breadboard.
You're the one that was on the Teams. There was a breadboard, the image of it.
Yeah, true. Yeah.
Should I copy of that one?
No, just build it from the schematic that you see right here. Yeah, because you have to learn to, let's say, transform a schematic like this, the circuit in this schematic, to your breadboard. Yeah, that's space enough. You can build it over there. And in series with R1 and R3, you put a LED, light emitting diode. And when you build it correctly, the LEDs blink alternating. So first the left one, and when the left one goes off, the right one goes on, etc., etc. Okay, for Yara, who's at the record, then I can go back to the schematic for the second year term. Let me check. We are working with operational amplifiers. And this is the first schematic. Remember, Yara?
Yeah, this looks familiar.
You started building this on your breadboard, remember?
Yeah.
Okay. Would it be convenient if I would explain how this works?
Yes, please.
Yeah, okay. So let's first, if I simulate this, we can see the output. Okay, here it is. Let's do this again. Make it like this. And then like this. Okay. And I'll make this more thick so you can see it a lot better. So what do we have here? This is the amplifier. It's operational amplifier. And it's connected to the amplifier two resistors, RF and RG. if I'm going to open the electronics, yeah, there it is. I'm going to open this. And I'll go to the page where we can find the information I'm going to talk about. Let's elaborate on that. Here it is, this page. Okay. In the beginning, we analyzed just the operational amplifier itself. That means if this input is, what does it do? The basic of this operational amplifier, when there's a difference between V1 and V2, then you have an output signal. That means you can see it as a comparator. It compares this input with that input, and when there is a difference, there's an output. That's the basic operation of the operational amplifier. Yeah, and if you use it without any feedback, and they call this feedback, this connection here, I have two resistors on the output, and a little bit of the voltage, the output voltage, is over Rg, and it's being fed back to this input. And why would you use feedback? If you do not use feedback, then the difference between this pin and that pin is being amplified by approximately, theoretically, infinite, and in reality about, depending on the specific type of operational amplifier, 100,000 times or 200,000 times. At least many, many, many times. And what happens, the power supply is what limits the output signal. So the output signal can never be larger than the voltage of the supply voltage. And if we go back to the first analysis just with DC, let's go back to that one. I can use this one. Here we have an AC in the input, that's correct. What happens if this input signal, the sine wave becomes positive, then the inverting input, yeah, is higher than this one. But because this is the inverting input, the output voltage goes negative. How far negative? It's being limited by the power supply. So you can never go further than minus 15 volts. And it's a little bit less than 15 because the operational amplifier is not perfect. It's not ideal. We go back to the first schematic. Let's just go through them. That's the history, the website, the packages here. Let's just go through it slowly. So if we just look at the triangle of the operational amplifier, here it is, the symbol. Are you still with us, Yara?
Yep.
Okay. When there's a difference, see what it is. As long as there's a difference at both inputs, an output signal will follow. So the difference is between the minus input and the plus input. So you could say it's just a comparator. The operational amplifier compares this input with that input, and when there's a difference in voltage, and there's an output. That's the basic function of the operational amplifier. So if the inputs are the same, if I would connect 10 volts to this input and 10 volts to that one, then 10 minus 10 equals 0, and there's no output signal. So if there has to be a difference between these two, then you have an output signal. Well, and there's something else here. The operational amplifier, the op-amp, does everything within its power to get the difference between its inputs, both inputs, to 0. So it will give an output, and it wants to do that, and this has to do with feedback, because when there's no feedback, this will never happen. Because there's no feedback, so you can deliver as much as output current as you want to. It doesn't change anything because now there's no feedback. It will become more clear later on. Let's continue. That's a, don't worry if you don't understand it yet. We'll go to the next one. Just skip this for now. It's all about the different types. And here you see the theoretical. This is all theoretical, like an ideal situation. There's no input current, 0. There's no input offset voltage, also 0. The input impedance is infinity, so enormously large. The output impedance, the output here is 0, and the gain, the amplification factor of the amplifier itself, is also infinite. It's huge. That's an ideal situation. Okay. I'm going to the first, the power supply. So again here, as long as there's a difference, both inputs and output signal will follow. How can we analyze this? Now you see this picture. This connection is a power supply connection, V+, and V- is also a power supply connection, and inputs are signal inputs. Just to be sure that you know the difference between these two. This is for signal input, and this connection, and that one is for power supply. Let's continue. It's like the sandwich we need. Without any power or inputs, we can't function. The same goes for electronics. And all electronics need a power supply. So when you start breadboarding, it's just wise to first connect, always first connect the power supply, of course, to the correct pins of the operational amplifier. Okay. Then there are two signal inputs, the inverting input. The minus symbol says that it's the inverting input, and the plus symbol says that's the non-inverting input. What did I write here? The power supply is not shown. Oh yeah, this is without the power supply. So the connections are there, but the power supply itself is not drawn in this schematic or this image. And here for reference, the op-amp will be connected to a symmetrical power supply of plus 15 volts and minus 15 volts. In the beginning, we're just going to use this. Later on, the voltages may become smaller, and that's because the newest chips, newest integrated circuits, operation amplifiers, they can work with a lower voltage, and then the frequency can increase. You can use faster signals. Why? Because you are sooner at 1 volt or 2 volt than at 15 volts. This takes a little bit more longer. But later, for now, we just say always plus and minus 15 volts. And then here's a proposition. When the minus input, so that's this one here. When the minus input is at ground or 0 level and the plus input is positive, the output rises extremely fast to V+. And V+, that's meant the positive voltage. So that would be the plus 15 volts. And then when the minus input is at ground level or 0 volts and the plus input is negative, the output descends extremely fast to the minus V minus, the negative supply volts. So, and here you see the two propositions. When the plus input is higher than the ground, the output goes to plus 15 volts, and you'll see it in the graph soon. And when the plus input is lower than the ground level of the minus input, the output goes to minus 15 volts. Then when we test them in PSpice, and this is, write all your findings and schematics and simulations in your personal analysis document. Here you see it in the schematic. And now you see that the plus and minus power supplies are connected. So plus 15 volt goes to this pin number 4 of the LM324. And the minus 15 volt goes to pin number 11. And what's been done here, these two are the signal inputs, pin number 3, pin number 2. And pin number 2 is connected to your 0 reference. Pin number 3, the non-inverting input, is connected to a plus 1 So what will happen? This is at 0 level, 0 volts level. This one is at 1 volt level. And then the output will rise really fast to plus 15 volts. So we can see here it says again, just for reference, we use a plus or minus 15 volts symmetrical power supply. You can see that here in the schematic. And then, oh yeah, in the picture, the op amp is flipped. You can see the plus sign on. That doesn't do anything. That doesn't make a difference. This is just about drawing. In this image, the plus inputs and the minus inputs are like this. So the plus on the lower side and the minus on the top side. And here they are interchanged. So the plus is on the positive on the top side. It doesn't matter. That's just how the drawing has been made. Let's continue. Oh yeah, of course, when you put it in PSpice, you have to place a voltage marker here and there, the input and the output, and you can see the effects. And here I've put all the information of the transient analysis, the setup. And here you have the schematic and the output in the background. So what do we see? Oh yeah, I'll switch off this one, otherwise people will disturb us all the time. This green line represents the plus 1 volt, this one. And of course, it's just a horizontal line because it's a DC. And this red line is the output. And you see, why does the output goes to positive, to about the plus 15 volts? Because this input is connected with a 0 reference, and the non-inverting, the plus input, is connected to the plus 1 volt. And then the output rises really fast to the maximum level. The maximum level, it's not exactly 15 volt, 14 point something. That's because the operation amplifier is not ideal. You have a little voltage loss on the inside of the operation amplifier itself. Yeah. Later I can show that more in detail when we look at the schematic, but for now, that's okay. Let's go to the second proposition. Here you see what I just explained. Theoretical, this would be plus 15 and this would be minus 15. But because the operation amplifier is not ideal, you have a little voltage loss because of the internal, the power amplifier inside the schematic of the operation amplifier itself. So the voltage will be a little bit less. We just saw that here. This is about 14.1 or 2 volts. Okay. Internal losses of the operation amplifier. Here once again. Oh, here you can see it. It's the basic schematic of the output stage of the operation amplifier, and there are 2 transistors, Q1 and Q2, and in series. The resistor is always in series so that the current will not be too large. There's a little voltage drop over R1, and there's also a little voltage drop over the transistor Q1. And the same goes for the negative side if the signal is negative. The input signal, if it's a sine wave, there's a little voltage drop over R2 and a little voltage drop over Q2. Okay, let's continue. Here we changed something. Now, make sure you can see V input is now not plus 1 volt, but minus 1 volts.
Sir,
Yes.
may need a little teaching on how to read it. Because I know some of the talk going, the more it gets down, it gets complicated.
Okay, gonna help a student. He is in the lab. I'll be right back. One moment, please.
What's up, lady? You need help with that reading?
Oh, they can put.
Yeah,
Oh, yeah.
because I know it, I just don't know how to read it onto the board.
Dan kan je zo weer nee, nee,
Okay, we're back. Now we change the input. As you can see, V input, this one, is now -1 volt. What happens then? So when this was +1 volt, the output would go to almost +15 volts. And what if this becomes negative? -1 is lower than this 0. So let's go see what happens. And what do we see? The output goes negative. And you can also see now it almost goes to its 14.9, almost 15 volts. And that's because the operating amplifier, it's not ideal, but it's also not perfectly symmetrical. Because when this was +1 volts, then it went to 14.1 volts. And when it goes negative, this one, -1 volts, the output is almost 15 volts. So you see it's not really symmetrical. Proposition 2 is confirmed. And here you can see them together. Proposition, the +1 volts, the output goes to almost 15 volts, 14.1, this one is 2.2. And when this input becomes negative, the output becomes negative. Okay, that's proposition 1 and 2. And you see the asymmetry. Positive one goes to 14.1 and the negative one to -14.9. That confirms the output is not fully symmetrical. Okay, we just mentioned that before. Okay. Then proposition number 3. What do we do now? We put the voltage to the input, we name this the signal, at the inverting input. If we look at proposition 1 and 2, this V input was connected to the non-inverting input, and this 0 reference was connected to the inverting input. Now we change it around. That means the V input is now connected to the inverting input, and the 0 reference is now connected to the non-inverting input. And what happens now? Let's look at the output in PSpice. So we have a +1 volt connected to the inverting input and a 0 reference. We call it a ground, but it's not really a ground. The 0 reference connected to the non-inverting input. And what happens? You see, here you can see the green flat line, that's the plus. This is a 0. You can zoom in a little bit. This is a +1 volt, and the output goes negative. And of course, again, limited by the power supply. So you can see proposition number 3 is confirmed. That was a short interrupt, just close the door. Some students were really loud. So proposition 3, that's +1 volt on the inverting input, and the 0 reference is connected to the non-inverting input, and we see the output goes negative. You see, it's just like an inverter now, because if the inverting input is higher than 0, 1 volt higher than the 0, than this 0, the output goes negative because it's connected to the inverting input. Let's continue. Proposition number 4. Hey, this should be proposition. Oh, forgot to translate this. Proposition number 4, we connect a -1 volt to the inverting input, and the output goes positive. Remember from math, -1 multiplied by -1, so minus times minus becomes positive. We can see that here we have this is a 0 line here, -1 volts connected to the inverting input, so minus times minus, and becomes positive. And that's proposition number 4 confirmed. Okay. And here you have them all together, proposition 1, 2, 3, 4. You can see the plus input, if it's positive, the minus input, the inverting input connected to ground, the output will go to the positive voltage etc. for proposition 2, 3, and 4. And here you see all the schematics to proposition 1, 2, 3, and 4. If we would connect an AC voltage, so a sine wave, and the first schematic, then you have proposition 1 and proposition 2 in one schematic, because if this is a sine wave, the input starts to be positive, and then when the sine wave will change polarity, it becomes negative, and that is this situation. So when you use PSpice, you can do this. You can use the DC voltage as an input, and when you want to breadboard this, it's more convenient to connect an AC voltage at the input for this and that, and here too it's the same. So then you have proposition 1 and 2 in one measurement when you connect a sine wave and the input, because the sine wave changes polarity all the time. And for proposition 3 and 4, you have the same situation. Only what difference is that you put the input sine wave at the inverting input. So here on the non-inverting input, the signal, and here at the inverting input, the signal. And that's the analysis of the 4 propositions, of just the basic analysis of the operational amplifier itself. Then we're going to connect the sine wave. Here I've placed the information. How do you set the VSIN in PSpice? You see a 1 volt top and a frequency of 1000 Hertz, or 1 kilohertz, 1K. And here is again the first schematic with the DC still connected. And here it says we replace the DC voltage with a sinusoidal or sine wave AC voltage. And you can see proposition 1 and proposition 2 can be tested at the same, because of course an AC voltage, the polarity will change, like I mentioned before. Again, proposition 1 and 2, and now you can test them both at the same time, because we have here the AC as an input voltage. And let's go to the output. Here we see the output. When the input of the non-inverting amplifier goes positive, the output goes positive. And when it goes negative, the output goes negative. Proposition 1 and 2 for AC are confirmed. And the same when we change that. You see again the schematics with DC, the old ones, and we change that. We'll exchange the power supply of the signal with the V sinus, and we have proposition 3 and 4. When the positive signal is connected to the inverting input, the output goes negative. You can see that here. Positive inputs, the output goes negative. And when the input goes negative, the output becomes positive, just like an inverter. Or you could say 1 becomes negative and the negative number becomes positive. It's an inverter. And just to recall, as long as there's difference at both inputs, then output signal will follow. And the operation amplifier does everything in its power to get the difference between input 0. We'll check this point when we will have a look at feedback, because this is still all without feedback. There's no connection between the outputs and one of the inputs. It's all open loop amplification. There's no loop between the connection between the output and the input. And a short intermezzo about slew rate, the speed of the operation amplifier. If you look here, if you have an input signal like this, it always takes time for an electrical signal to go through anything, a wire, a chip like operation amplifier, a capacitor, a coil, a transistor, etc. So slew rate says how quickly can the output of the operation amplifier respond to a change in the inputs, and it always takes time. If you have a very slow operation amplifier, this slope will be more like this, less steep. This is relatively steep. And when you have a very fast operation amplifier, that means the value of slew rate is very high. The value is given in volts per microsecond. then this slope would be a lot steeper, almost going straight up. If you do measurements of the slew rate, and you do that by increasing the frequency of the signal, then you would zoom out on the, zoom in, I should say, on the horizontal axis if you want to see the slope. Later, more on that. And of course, if you have a sine wave at the zero crossing, the signal is the most steep at the zero crossing. Yeah, so then you need the fastest op amp, because the speed is maximum crossing the horizontal axis, changing polarity from positive to negative and back from negative to positive. These are just two pictures of the dual in plane package of the LM324 and the QA741, both let's say old operation amplifiers, one of the first. And here you have the schematic. This is the second one, of course, proposition 3 and 4 together, because this is the sine wave, and you see when the input becomes positive, the output goes negative, and vice versa. When the input goes negative, the output is positive. The slew rate. This is a little bit of the data sheet now of the website of Texas Instruments, and you can read here the slew rate is 0.5 volts per microsecond. Yeah, you might think, oh, that's fast because it's in microseconds, but trust me, this is really slow. There are much faster operation amplifiers, and the fastest one from TI, it's Texas Instruments, you can see ti.com, is about 18,000 volts per microsecond. Not 0.5, but 18,000. That's a lot. They are being used in smartphones and stuff like that. Yeah, they go to frequency of about 7 gigahertz. So that's extremely fast. Let me see. Oh yeah, this is little. You can read this later on. The Earth will explode if the ideal operation amplifier would exist. Measuring, you do that in the lab. And I will give more information while your students are in the lab building this schematics. But most students find very difficult. How do you connect these wires to make a positive, symmetrical power supply? What happens here? If you look in PSpice, you see the plus sign over there and minus sign over there for this power supply, and here again a plus over there and a minus over there. What's been done? The minus connection of this power supply is being connected to the positive one of this one, and you'll do the same in the lab. This is a picture of the Rigol power supply in the lab. You connect this minus connector via this wire to the plus one of the other one. It's the same like here in SPICE. This little wire, minus one of this one, goes to the plus one of the other one. And then we just call this connection the zero reference. Why? This connector is, if they are both set to 15 volts, this power supply and this connection, then this point is the 15 volts lower than this point. And if I call this 0, then I can call this minus 15. In the same way, if this is connected, I can call this, because this point is 15 volts higher than this one, and I call this plus 15 volts. And then you have minus 15 volts and plus 15 volts as a reference to this 0 point. And you see how you connect this. You know from the data sheet what pin is what. Pin 1 is the output, pin 2 is the inverting input, pin 3 is the non-inverting input, pin 4 is for the positive power supply, and here pin number 11, 14, 13, 12, 11 is for the negative power supply, the minus 15 volts. Okay, and for the signals, you have here When I made this drawing in Microsoft Word, just used these two lines, but there's a special connector, a bayonet connector. You know the cable by now in the lab, the red and black, and the cable is red. You just click it on here, and then you have to remember that you have two crocodile clips over here, and that the crocodile clip itself is being connected to the 0 level. This is being connected like this, goes up and is connected to the 0. And the other one is being connected here to the operation amplifier, pin number 3, the non-inverting input. If you want to see the signal also on the oscilloscope, and that's what you want, you also have to make sure that it's being connected to this channel of the operation amplifier, and the cable that's connected on the on the oscilloscope has a crocodile clip, and the crocodile clip is the 0 reference, and the other connector is like a small hook that's being connected with the signal itself. Then you would see this is not the correct picture. This is just a picture of the oscilloscope. So this is not this looks like the output in open loop. Yeah, so it shows a signal that looks like the output. It doesn't show the input, because the input signal would be a nice sine wave. Let's continue. Here you can see what pin is what. So there are 4 operation amplifiers in the LM324 chip, and be careful to really carefully read all the numbers. What's that? This is output, this is the inverting input, and the non-inverting input of this second operational amplifier. Okay. And some notes about the lab supply. You can push these 2 buttons to activate the voltage that you've set here. How do you set the voltage? When you press number 1, it's been done here. The left channel 1 will highlight. Here you can see the 1, here you can see the 2, and then the 3. So when you press this button, this channel highlights. It's being connected with these 2 connectors when you push the on button, and when you click it again, you disconnect these 2 connectors of the power supply. And when you press this button, you can see it has been pressed. This highlights, it says volt, so you can set the volts. And here you see that the left digit, the digit number 3 here, has been highlighted. So you can use the horizontal buttons with the arrow, this one and that one, and then you can choose any digits. When you've selected specific digit, you can turn this round knob clockwise for increase and counterclockwise to decrease the number of the specific digits. And so you can set the voltage that you want to have. In this specific case, we set them both to 15 volts. You press both buttons on, and then it's 15 volts between these 2 connectors and 15 volts between these 2 connectors. Okay, let's continue. I'm going to skip this. These are the steps that you want to use, that you'll need for your writing your own analysis document. Skip them for now. The data sheet, skip them for now. I always advise students download. You can Google LM324, and then you press the spacebar once, you type datasheet, and then you can download this datasheet as a PDF. The datasheet is just a document that shows all the features, the characteristics of a specific component, in this case, the quad operational amplifier LM324. It says LMX24 because you have the 1, the 2, and the 324. And it says quads because there are 4. Quads means 4 operational amplifiers in one chip. And you can see a chip or package. Different types of package exist. That means the PDIP is for through hole, and the SOIC and the TS SOP is for SMD, surface mounted design. That means there's no hole in the printed circuit board. The chip is being soldered on the top side of the printed circuit board, and through a hole, then the pin of the package goes through the printed circuit board and you solder that on the other side. Then you have a component side and a solder side. Chapter 3, the basic circuits with operation amplifiers. You already know this one. So let me see. Yeah, to get the gain that is desirable, we're going to feed the output signal back to the input. More on that later on. And then you get that the resistance of ohmic resistors is quite stable in terms of temperature. The gain of the op-amp also becomes stable if the gain depends on the resistors, because they are relatively stable. If you do not use feedback, like in this schematic, and the temperature will change, think of the summer, can become 40 degrees or more, and in the winter it might freeze a few degrees below zero, a few degrees Celsius. Then this operates amplifier, because it's an active device, the characteristics will change with temperature, and you don't want that. So resistors are relatively stable. If you see that the temperature will change, the value of the resistance will may change 1% or 1.5%. If the temperature changes for the operation amplifier itself, the characteristics may change by 10, 20, 30, or 50%. So if you could find a way, and the way is feedback, you'll see that later on, if you find a way to make the amplification factor dependent on the resistors, on external components, resistors, then the amplification will be a lot more temperature stable, so independent of the changing temperature. Let's continue. Non-inverting amplifier. As the signal is in phase. Non-inverting means that the input signal and the output signal are in phase. In phase means when the input signal, let's say this one is the input, the dotted signal, when it starts to rise from 0 to a positive value, that the output will also rise from 0 to a positive value. In this case, it's been amplified because the amplitude of this line, the non-dotted line, is larger, has a larger amplitude than the input signal. And of course, when it goes the other way around, if this is the input signal and this is the output signal, then it's out of phase. You see top signal, this one is in phase, and the bottom signal is out of phase. Okay, let's continue. This is the first schematic in which we use feedback. That means you have two resistors connected to the output of the operation amplifier, and this is the 0 reference. And the voltage over RG is being fed back to the input. So, and here you can see with the non-inverting op-amp, the signal is applied to the non-inverting positive input of the op-amp. More or less an infinite large impedance, because you see here Zin is very high. So if you would look from left to right, you can see that further on. Yeah, this is your eye. You look from the left to the right, you would see. Think of it as if you would connect a voltmeter or an ohms meter. Then you can see this as a connection, like a wire, and that you will only measure RG. And if you look from the outside, from the right side into the amplifier, and imagine you would connect an ohms meter here, then you measure RF in series with RG. Well, let's go back. There's no input offset voltage. Okay, that's true. And the output of the op-amp sends current through RF until the negative input of the op-amp is at the level of V in. So the operation amplifier just sends current through this resistor, and this is in series, so the current goes also through RG. And when there's more current going through RG, the voltage over RG will rise, will increase, and then the voltage at this point will also increase, and this will go to 0, because if you put a signal, an input signal at V as V1, this V is an input signal, there's an output current. The current will go through RF, through RG, and then the voltage over RG will increase. That means that the voltage at this point will also increase. And that's the text that's in, let me see, let me check. Yeah, on page number 49, let's just remember that. I want to show you something else. This one. The op-amp does everything within its power to get the difference between both inputs to 0. And this has to do with the situation when there is feedback. So once again, the op-amp does everything within its power to get the difference between both its inputs to 0. So we'll go back to page number 49. If you have a look at this again. So the operation amplifier, in the situation of feedback, and that's here the connection between this input and this RG, the operation amplifier keeps on supplying current that goes through RF and goes through RG. It will keep on doing that until the voltage over RG is the same. So that will be, because this is just a wire, the voltage at this point will be the same as the voltage at this point. Why? That's the characteristic of the operational amplifier. Remember, as long as there is a difference, there's a VE, so a difference between the voltage at this point, the non-inverting input, and the voltage at the inverting input. As long as there's a difference, and we call it VE, then the operational amplifier will supply an output signal, an output current. But the current is going through RF and RG, and if the current goes through those two resistors, the voltage over RG will keep on rising, keep increasing, and then the voltage at this point will also increase, and it comes more and more and more closer to the voltage of Vn. That means eventually VE will become 0. And when there's no difference between these two inputs, then there will be no output. And that's how this schematic functions. So if there's a difference here, the operation amplifier will supply a current that runs through both resistors. If there's a current running through both resistors, then voltage over RG will increase. The voltage over RG will increase. The VE, that's the difference between these two, will decrease, will become smaller, will decrease until it's 0. And when the difference here is 0, that's the characteristic of the operation amplifier, then it will do nothing. There will be no output current. And that's how this feedback system functions. And we use this effect in a million of applications. You can do so many things with that. Yeah. Okay, let's continue. Then we see the transfer characteristic. That means, just some words, how many times is a signal being amplified? That's what's been meant with the transfer. That is, I can say the transfer is V out, and the transfer of the circuit is V out divided by Vn. So for instance, if the output would be 10 volts and the input 1, 10 volts divided by 1 volt means an amplification factor or transfer of 10. It has no unit because you divide the voltage by voltage, and then the units can be eliminated. So if I have a look, you can write Vn as Rg, and you can write V out as voltage over Rf and Rg. So if we just write resistors, then you have V out becomes Rf plus Rg, and Vn becomes just Rg. That means V out divided by Vn becomes RF plus RG divided by RG. And beware, you know RG divided by RG equals 1. If you look here, V out divided by V in, I can write RG plus RF divided by RG.
Yeah, I've seen it.
And RG divided by RG equals 1 plus this signal, this plus sign is just because it's over here, plus RF divided by RG, just like it's here. And if both resistors are 1K, in this situation, 1K and 1K for RF and RG, then you get 1 plus 1K divided by 1K, or 1000 divided by 1000. But 1000 divided by 1000 equals 1 plus this 1. That means, going back to the schematic, the value of RF is the same as the value of RG. In this case, both 1K, amplification factor or the transfer equals 2. And if you have a look here, this is the schematic in PSpice. You know the symmetrical power supply from before. And here you see RF and RG. Again, the transfer function, or just abbreviated just shortly, the transfer 1 plus RF divided by RG. And here it says RF and RG both 1K. The transfer becomes 1 plus RK, or 1K divided by 1K equals 2. And here you see it in PSpice. So we give the input signal of plus 1 volt. The red one is the input signal, and the output signal goes to 2 volts. Okay. It's now just a few minutes past 5 o'clock, so I'll stop this recording for now, and you can watch it back as many times as you like. I hope you learn how this schematic works and you understand the principle of feedback, and that's a very important principle. Okay, we'll come back to that later on. Good luck learning and keep on smiling.